Hello again. In this video, we're going to start talking about the material from Chapter 3, which is on derivatives. Now, building on the idea of a limit, which we talked about in Chapter 2, we're going to introduce the two most fundamental operations in calculus. One is known as the derivative, and the other is known as the integral. Now, we'll talk about the integral in Chapter 5. But for now, we're going to introduce this idea of a derivative. And in order to talk about a derivative, we first need to talk about the average rate of change in a function between 2 points and the instantaneous rate of change in a function at a single point. And then we'll introduce the formal definition of a derivative. And then we'll start talking about some of the rules that we can use to find derivatives. And then eventually, we'll start applying the derivative to solve problems in calculus. Okay, but for now, let's talk about average rate of change in a function between 2 points and the instantaneous rate of change in a function at a single point. Okay, so suppose we have some function f of x, the graph of which looks like this. And let's say we want to find the average rate of change in this function between this point A and this point X. Now, the way we're going to find the average rate of change in the function between those 2 points is we're going to draw a line between those 2 points. And so the 2 points we're talking about are located at A, comma, f of A. And we're going to label that as point P. And then this other point, X, comma, f of X, which we're going to label as the point Q. Okay, so we're going to draw a line between those 2 points, which is called a secant line. A secant line goes through 2 points on the function. Okay, and so we're going to find the slope of that line, and whatever the slope of that line is actually the average rate of change in the function between these 2 points. Okay, well, how do we find the slope of a line? Well, the slope of a line is simply the rise over the run. So the rise in this function, as you go from A to X, the rise would be the change in the y value, so the difference between this y value, which is at f of x, and this y value, which is at f of a. Okay, so the rise is simply f of x minus f of a, whereas the run is simply x minus a. And so if you divide those, rise over run, you get the slope of this secant line. And we're going to denote the slope of the secant line using an m for slope and then a subscript sec for secant. Okay, but whatever the slope of this secant line is, that is the average rate of change in the function between the point A and the point X. Okay, and it's given by this formula, which is simply the rise over the run for this line. Okay, now let's try to find something different, which is called the instantaneous rate of change in the function, and we're going to find it at this single point, A on the function. It's actually at A, comma, f of A. So we're going to find the instantaneous rate of change in the function at this point here. Now here's how we're going to do that. What we're going to do is we're going to look at the slopes of these secant lines between these 2 points. As x approaches A, we're going to try to determine what the slopes of those secant lines are approaching. And whatever number they're approaching will be the instantaneous rate of change in the function right when we're at this point A. Okay, so let's see if we can't sort of figure out what that would be. So we're going to let x get closer to A, and you can see as x is getting closer to A, our secant line is beginning to change a little. And you can see the slope of the secant line is changing. In fact, the secant line is beginning to approach this other red line, which by the way is called a tangent line. And the slopes of these secant lines are beginning to approach the slope of this red line, again, the tangent, it's called the tangent line, at P. Well, the slope of this tangent line is actually the limit of the slopes of the secant lines as x is getting closer to a. So it's actually a limit. Okay, so and we're going to denote the slope of the tangent line, m for slope, and then subscript tan for tangent. That's equal to the limit as x gets closer to a of the slopes of these secant lines. And remember, this is the formula for the slope of a secant line. Okay, so whatever this limit is the slope of the tangent line right at this point A, which is also the instantaneous rate of change in the function right at A. Okay, so that's what we mean by the instantaneous rate of change in the function at A. It's actually the limit of the secant lines as x gets closer to A, which, by the way, is also the slope of this tangent line. Okay, so having said that, let's look at an example where we use some of this. So let's look at example 1. So in example 1, a rock is launched vertically upward from the ground with an initial speed of 96 feet per second. The position of the rock in feet above the ground after t seconds is given by this position function. And we're supposed to find the instantaneous velocity of the rock 1 second after launch, and then find the slope of the line tangent to the graph of the position function right at the point P, where P is this point 1, 80. And then after that, we're supposed to find an equation of the tangent line. Okay, so let's start with part A. We want to find the instantaneous velocity of this position function right when t is equal to 1. Which, by the way, is the same as the slope of the tangent line when t is equal to 1. And that's given by this limit, right? Now, in this case, our function is actually a position function. And so if you find the instantaneous rate of change in this function right at this point 1, 80, you're actually finding the instantaneous velocity of the object right when t is equal to 1. Okay, so if you have a position function and you find the instantaneous rate of change in the position function, you're actually finding the instantaneous velocity. Okay, and then for us, our variables change here. Instead of x, our function depends on t, and instead of f, our output is s. Okay, so if you convert everything over to the correct letters, this would be s of t instead of f of x, and then this would be s minus s of a instead of f of a, and then instead of t minus a, it would be x minus a, and the limit is t is approaching a. Okay, so they're just changing our variables here because our function is in terms of t and s. Okay, so let's find this limit. So it's the limit as t approaches 1, because we're approaching this point t equals 1. And s of t is this position function. Minus s evaluated at 1. All over t minus 1. Okay, so for us, a is 1, because we're finding the instantaneous velocity right when t is equal to 1. Or the instantaneous rate of change in the function when t is equal to 1, right? They're the same thing. All right, so s of 1, of course, is 80. If you plug a 1 into here, you get 80. So at 1 second, the object's located at the 80-foot mark on the number line. And so we're just left with this limit here. Now, to evaluate this limit, we have several options. We could create a table. We could look at the graph. or we could try to use direct substitution. Now, in a previous video from section 2.1, we had this exact same problem, and we found the instantaneous velocity when t is equal to 1 by creating a table. So this time I'm going to find it by using direct substitution. Okay, so if you plug 1 into this, you'll get 0 over 0. So it's indeterminate. And when it's indeterminate, that means we have to change it to a simplified form until it's determinable, and then try direct substitution again. So I think the thing we need to do here is just maybe factor out this negative 16, which isn't common. And then you're left with t squared minus 6t plus 5 all over t minus 1. And then we can factor this trinomial. This factors into t minus 1 times t minus 5, which is great because then the t minus 1s will cancel. And now we can try direct substitution to evaluate this limit. When you plug a 1 into here, you get negative 4, and then negative 4 times negative 16 is positive 64. And this the distance is being measured, the position is being measured in feet, and the time is being measured in seconds. So this is feet per second. Okay, so this is the instantaneous rate of change in the function when t is equal to 1. But since this is a position function, it's also the instantaneous velocity of the rock when t is equal to 1, which is also equal to the slope of the tangent line to this function when t is equal to 1. Okay? All right, now for part B, and if you go back and check this, that's the exact same answer we got from the previous video in section 2.1, where we used a table to evaluate this limit. Okay, so going back and looking at part B now, we're supposed to find an equation of the line, of the tangent line in part A. Okay, so we know the slope of this tangent line, right? It's 64. All right, the slope of the tangent line right when t is equal to 1, right? That's equal to 64. And we know a point on this line. We know the tangent line goes through this point 1, 80 because we're trying to find the tangent line at that point. Okay, so we know it goes through this point. And so we can use a point slope formula to find the equation of this line. Okay, m is 64, that's our slope, and then x1, y1 would be 1 and 80. And then just solve for y here, distribute the 64, so you get 64x minus 64, and then add the 80 over to the other side, and you just get 64x plus 16. Now, it may be more appropriate to write this in terms of t, because this our independent variable is t instead of x. Okay, but either way, this is the equation of our tangent line, right when t is equal to 1. Now, let me show you a graph of this. Okay, so here's our position function. It's just a parabola that opens downward. And right when t is equal to 1, the tangent line looks like this, right at that point. And the equation of that line is 64t plus 16. So you can see that it has a positive slope, a pretty big positive slope of 64. So this should be increasing very rapidly, which it looks like it is. And then the y-intercept is 16, which appears to be correct, at least roughly speaking. Okay. Okay, so just to kind of wrap this up, when you find the slope of the tangent line at this point, not only are you finding the slope of the tangent line at that point, but you're also finding the instantaneous rate of change in the function at that point. And in this case, since this function is actually a position function, you're also finding the instantaneous velocity of the object at that point. Okay? Okay, so the instantaneous velocity of this object is 64 feet per second, right when t is equal to 1. Okay, in the next video, we're going to look at some alternative definitions for average rate of change and instantaneous rate of change. And then the video after that, we'll start talking about the derivative. Okay, I hope this video was helpful. Thank you for watching.